Hello and welcome to everyone. I hope you're all doing fine this evening, and thank you for joining us with this terrific event we're having tonight. Why is this a terrific event? Well, because it's a live Teams event, and our speaker will be presenting live from Maryland, USA. That's the first time I think we've tried that. And also it's terrific because of the subject that he will address. The Joint Polar Satellite System, the JPSS space program, monitoring and dealing with climate and environmental issues. So he will be speaking about space, about the environment, about climate change, all key subjects that we're all, of course, passionate about. This event is organized in partnership by IPSA, or Aerospace Engineering College, and the Paris branch of the Royal Aeronautical Society. So for those who may not be familiar with the society, this is a very old society. It was actually founded in 1866, and it's the world's only professional body dedicated to aerospace around the world and contributing to its development. It's actually a forum, a central forum, and a huge network, about 25,000 members worldwide, with branches all over the world. There are 2 branches in the US. We have 2 in France, in Paris and Toulouse, 5,000 young members, so very futuristic organization, and headquartered in London, but like I said, with branches everywhere. So we have a very strong partnership between IPSA and the Royal Society, or corporate partners. And actually, I do represent IPSA at the Paris branch committee. What we do, we use this partnership to organize events with our students, visits, trips, competition, and especially conferences. And of course, we take advantage of this huge network of the society to find high-level speakers about aerospace subjects. So now let me introduce and I want to express all my gratitude to our speaker tonight, Dr. Pey-Schuan Jian, who is a programmer analyst at NASA, the National Aeronautics and Space Administration, and NOAA, the National Oceanic and Atmospheric Administration. How did we meet him? Well, just the anecdote, he happens to be a friend of one of our teachers at IPSA, Caitlin Suarez, and he has kindly offered to present to us his work on the Joint Polar Satellite System operations. Dr. Jian has a PhD in physics and photonics and a Master of Science in physics, and he's had a tremendous career as an engineer, a researcher, a mathematician, a scientist, developing algorithms for defense, working on data systems, working a lot for the environment. And again, he's presenting to us live today from Maryland, USA. So, Dr. Jian, thank you very much again for being with us today. And now I will hand it over to you.
I don't know if anyone could hear me.
Yes. Mm-hmm.
Could you?
Yeah, go ahead, okay. We can hear you. Go ahead.
Unfortunately, I cannot see the screen right now. Okay. There's some technical difficulty. The PowerPoint that you are having probably will be different from the PowerPoint I have prepared for today. So I will do my best to describe what I'm trying to present. Okay, so basically,
I'm sure you do great.
There's let's see if the I'm trying to join this Teams again. Hopefully,
you're having
if
technical
this,
problems with
I think so I started to have trouble when I was trying to.
Just make your presentation, and Florian can play the slides for you. Just go ahead with your presentation.
Okay, so what I'm saying is that the presentation probably will be different from what I have prepared for today, but that's fine. Okay, anyway, let's start.
Let's start. Yeah, please. Go ahead.
The next screen. I don't know what you have seen here, but this is the pages of my experience, but Philip already mentioned about that, so I will go on to talk about the meaning of the Jpss. Okay, it stands for Joint Polar Satellite System, and this basically is a restructured national polar orbiting operational environmental satellite systems. Okay, and during transition, eventually after the testing and experience with the success of the this initial joint mission MPP, okay, and then this satellite, the first JPSS mission satellite, renamed into the NPP or SMPP, named after the scientist Werner Edward Suivre, okay, the one who invented this spin scan radiometer. That is the foundation of the instrument vehicles. And what is about the GPS? It is mostly the data to inform numerical weather forecasting globally, also deliver critical events like hurricanes, tornadoes, and blizzards. And like what I said, the initial MPP satellites works very well, and that's why there's JPSS 1 to follow. Okay, and the JPSS 2 and 3 and 4 are scheduled to launch in the near future. And the next slide is just to show the launch of the JPSS 1 in the year of 2017. Okay, after the launch, once the satellite reached the destined orbit, and after the post-launch calibration and all sort of testing, when it starts to serve, then this satellite so officially this JPSS 1 is called NOAA 20 now, which is 520 miles up above the Earth. And what is the polar orbiting satellite anyway? Okay, so this is the satellite trajectory on the diagram. Could you show this view graph for the JPSS 1 polar orbiting? And if you show the video, then you could clearly see the SMPP and JPSS 1 orbiting around the Earth. And next slide, you are going to see the trajectory of the NOAA 20 satellite. Okay, and like what I have said, the Jpss 1 or MPP surround the Earth 14 times a day, so it covers the entire Earth twice and in 24 hours, and this is the trajectory of the satellite. And of course, the polar orbiting, it once it descends from the North Pole to the South Pole, right? Then it will ascend from the South Pole to the North Pole again. So that's why this trajectory we have two features. One is ascending, the other one is descending. Okay, and now let's talk about the instruments that Jpss have. There are a few devices. The first one is called ATMS, Advanced Technological Microwave Sounder, and the other one, cross-track infrared sounder. Why is it called sounder? Because it is doing the vertical profile. Okay, that's why it is called sounder. And like what I have done in the past, the CO2 sounder to detect the carbon dioxide concentration of the Earth. And then there is also visible VS. Okay, this is visible IR imaging radiometer suite. Is medium levels of image and high resolution image to image the wind, particularly the prediction of the image of the hurricanes and so on. Now, next slide shows the description of the Jpss instruments. When I said Jpss, so far on services, one is an old satellite MPP or SMPP, the one named after the scientist Bernard Edward Suomi. Okay, and that one usually when the satellite get into the service, okay, when they reach the designated orbit and start to after the post testing, everything's fine. Start to serve that will give renamed into the number like JP. Like NOAA 20, and then the next one, Jpss 2, once here start to work, okay, then it will be named as NOAA 21 as well. Hopefully that will happen next year. And the 5 instruments in the Jpss satellite. Like what I said before, VS. Okay, VS means the visible plus a few channels of the IR to do the imaging of the hurricanes and to detect the fire, smoke, and so on. And then quiz. Cross-track, so you could see there's actually cross-application with some other instrument. Particularly, this quizzes cooperate with ATMs, the Advanced Technology Microwave Sounder. Okay, the purpose is to profile atmospheric temperature and moisture, and so combined with ATMS instrument as supported by the quiz, we are able to measure the rain, the features of the rain, and also the total precipitable water concentration. Okay, now the arms Okay, ozone mapping and profiles suite is to measure the concentration of ozone in the atmosphere. To provide information of how ozone concentration varies with altitude. Okay. This the first instrument, ATMS. This instrument actually is built, okay, by the Northrop Grumman corporations, not NASA. But I'm going to talk later. The instrument eventually will reach the Goddard Space Flight Center for inspection. And these ATMs provide some critical information like vertical moisture profile or vertical temperature profile with the air pressure as well. And so this is a sample of the product of ATMs. So this view graph, you could see the map for the ascending temperature profile observed by the ATM as okay. The result ascending and then descending. And this is unfortunately, I don't think that you could observe in this view graph. Here's actually a simulation of the hurricanes Florence observed by the ATMS, but processed by the microwave integrated retriever system. Okay. And next one, I'm going to talk about the cross-track infrared sounder CRIS. And this one is manufactured by Harris corporations, not Goddard. Okay, and it is provide the high resolution measurement of the with a very low noise equivalent differential radiance. Okay, this is called NEDN. This is a measurement with a error variance. Okay, right now we are on the page of the Jpss cross-track infrared sounder. I believe it's probably at around page 15 or yeah. This is a little bit difficulty in the sense that the view graph I prepared is different from what you have in the archive. So, but anyway, I'm just trying to say that the CRIS, the cross-track infrared sounder, provide 1,305 spectral channels for the long wave infrared, mid wave infrared, and short wave infrared. But once it is in the full spectral resolution, then we got 2,211 spectral channels for all three bands, and it provides very fine resolution to improve the vertical sounding, increasing both the radiometer and spectral accuracy. And like what I said, this usually cooperate with the ATMS to produce the vertical moisture profiles. Okay, just like what we have observed, the image, the motion of the rains and the total precipitable waters changing in time. Next slide. Next one is just to show the output product of the queries. Okay, here this roughly view graph on the page 16. Here queries show the brightness temperature. What is the brightness temperature? It's not a regular temperature, it is just the equivalent temperatures to maintain the same intensity of a black body energy. Okay, and use this. So this brightness temperatures is used to calibrate into the precipitation information and so on. Okay, and like a torpedo refractive index, and okay, yeah. So there's the product of the queries. Okay, next slide. So just show you the feature of descending. Okay. Next slide, we're talking about the VIAs, these visible infrared imaging radiometer suite. Like what I said, this is built upon the foundation of a spin scan radiometer that built up by the Wilnut Edward Suomi. Okay, this is the imaging tool, and this is manufactured by the Raytheon. I don't know if you heard about the company. This is a very famous company in the USA. Okay, the purpose of this, the product from the VIAs produce the cloud cover, cloud layers, and a lot of aerosol physical properties, and then ocean biosphere properties, snow and ice, and so on. And it is an imaging tool. Next slide. Next slide show you the VIA's global true color image. I would say this true color. Just for the tornado, with our visible raw eyes, we only could see the effect of tornado, but we cannot see what's going on of the tornado. But the IR could. Okay, it's so there's a lot of IR could observe what we cannot see, and you put it into the image with a true color, and then you are going to see the future, the circulation, and the intensity of the concentration of the aerosols. Okay, that's how we see the image of typhoon, usually with the true colors, that with the intensity presented by the different colors. Next slide. The final instrument is the ohms to measure the ozone profile vertically. And we have two features. So this is probably the view graph 20. Okay. For the J1 at this moment, the Jpss that is still on service is the J1. There's provide tall column spectrometer and nodule profile spectrometer, and they have a different response and to the ozone and SO2. Okay, so this instrument actually is manufactured by the Boeing Aerospace and Tech. Okay, so anyway, this is also the main company that built up a lot of spacecraft and detectors. Yeah. Okay. Next slide is just a future features mapped by the ohms and nadir profile radiance. Okay, and then what I said, this is to represent the ozone concentration. Okay, and next slide. I think so this is to show you the flight schedule of the JPSS tool. Okay, there's information from the JPSS ground information message service, and we plan to launch the JPSS tool next year, September 30th. And at this moment, the ATMs create ohms viewers for instrument. They have been mechanical and electrically integrated. Okay, and we're doing some testing, and also at this moment, I think start the in a few days we will start to do the satellite comprehensive performance test. Comprehensive performance test will start soon. So we'll hopefully by the September 30th next year, 2022, the JPSS tool could be launched on time. Now, how did we receive the JPSS data? Okay, and how the worldwide received the this stored mission data from JPSS before 1970. It was all provided by the ground station. Okay, space traffic data network. But you could imagine as the more space instruments on the sky, and it getting more vulnerable to process it in that way, particularly when the host country, for instance, in the very inconvenient place or it's occupied. Okay. It's just not so practical. For instance, I think I have said the next slide right up we are on the JPS as CG common ground system worldwide communication. Okay, so basically we need the help from TDRS. What is a TDRS? Is track data relay and ranging satellite. Okay, it's called TDRS. Okay, this is the idea created by Arthur Clarke. The idea is just so we have the carbon network satellite on the like in the west, in the east and the west, above the earthquake, and then we just need a few ground stations to relay the data to worldwide. Okay, so that's an idea. Unfortunately, I can get it. Next slide, I may provide a simulation for the data delivery through the Tdis, and so you could see that the satellite go through the send the data to the Tdis, and the Tdis send back the message to where, to like white sand compound and Arizona of the USA, and then that's where ENSOF receive the data, the stored mission data. And next slide is official. Next slide, and this is Jpss 2 ground system with the radio frequency links, and here's used to show that you know, in the Arctic and Antarctic, the two position, every time when the satellite goes through the survivor, okay, then in the Arctic, right, that will the satellite directly send the data to the survivor one station. Okay, that's for Arctic part. Once they reach the Antarctic, okay, then the Jpss satellites send the data to the where, to the Antarctic McMurdo ground station. Okay, and then the rest, okay, just rely on the Tdis. Okay, so there's only, the title is called Jpss 2 spacecraft SC to ground system RF links. Okay, and here is next slide. I'm going to talk about the one work I worked in the past to support a military satellite. At that time, I was the mathematician. I'm working on the algorithm development to optimize the signal to interference plus noise ratio to enhance the communication efficiency. Okay, so basically, I'll skip all of the theory. I just come out with to tell you the result is that I found a way to optimize. Basically, just mathematically, you need to maximize this SINR. Okay, and then from here, you could define the particular weighting functions and also the direction of every antenna, and also the link budget, the power needed to achieve this optimization. Okay, so I'm just to tell you, in the space network, there's one field of works in the loop. Okay, next slide. This is a built-in transceiver. I used to work in NASA Goddard. Okay, at the time I was building up a transceiver, and this is a laboratory. I just on the optical table, I was building up a laser transmitter and the receiver and the detectors, and so I'll show you in this telescope, and I am doing the experiment from the Goddard Building 32. I show you the location of the reference, which is micro tube. Reference for what? It's just a reference of carbon dioxide. So I could do the measurement of carbon dioxide concentration around the Earth. Okay, and so this is one of the detectors. Okay, and that's what I said. Next slide, inspection of instruments and the NOAA satellite. Here I'm just show you the view graph about the vertical. What it says. The 5 instruments, right? They are built by either Northrop Grumman, Harris, Bow, and Raytheon. But eventually they'll need to be assembled in the Goddard Space Flight Centers. Okay, so we're doing the inspection before the entire spacecraft to be sent to the California for launch. Next slide. Here is Jpss mission operation now. Okay. So I'm going to talk about the entire data flow from the, of course, the frontline Jpss satellite, where the detector receive the data. It's called stored mission data. Then we'll go through the 5 ground stations. Okay, read it by the Tdis, and then to the 5 ground stations worldwide. The one in the USA is called at Arizona. It's a white sand compound, and there's 5 places. Okay, and 1, 2, 3, 4, 5. Okay, and one is the comprehensive backup at Vermont. Okay, and this modules in the Antarctic, right? And then Savannah, Arctic, and Wallops, and Fairbanks, and so on. There's 5 ground stations to take care of accumulating the stored mission data. Okay, and here's just next slide. Next slide is space STDN configuration. It's what we call the space traffic data network configurations. I'm talking about the ground stations, and then there's a few places in the US, particularly. I think this is map to show you where is the white sand compound, WSC, and then the location of the mission center at the Goddard Space Flight Center. And this is in the USA. Next slide is worldwide ground stations. WGS is Wallops. Okay, that's in the Virginia, and AGS is Alaska, and then MGS is Mamados in the Antarctic. Okay, for the transmission S-band and X-band, and for the Arctic in Norway, there's Savannah ground station, and the AGO is the ground station in Chile. Okay. Now I'm talking about the stored mission data from this the ENSOF. Okay, so I need to clarify. The press I work is ENSOF, which is called that stands for NOAA Satellite Operations Facility. NOAA have a few facilities in the USA. One is in Silver Spring, there is a headquarters, and one is in the College Park. The one I work is at Switzerland, that is close to Washington, D.C. It's ENSOF. Okay, at ENSOF, the common ground station support management, data acquisition, data routing, and data processing. Okay, it was designed to be scaled, to be scalable for the future growth. Okay, and like what I have mentioned before. Okay, the acquisition, the data is acquired from the 5 ground stations hosted by the partner. Like what I have mentioned before, the McMurdo, right, Survival, Fairbanks, right, yeah, and of course in the USA that's a White Sand compound in Arizona, and this mission is implemented by the CCSDS link, space link extension protocol to define the application packet. Are you sure? Could you hear me? Could you? Could you hear me right now? I believe I already put on the microphone. Could you hear me? Hello? Hello?
Can you hear me?
Okay. Yes, I could hear. So
okay, now we can hear you.
Sorry about that. Okay. Now I'm on the page of SMD data flow. Okay. Yeah. Okay. So hopefully, I will just try to summarize this data flow to basically with the TDR's data relate. Okay, we gather the information from 5 ground stations worldwide. Okay, and this is in under the control of the ENSOF. We implemented the CCSDS. CCSDS means the Consultant Committee for the Space Data Systems. Okay, we use this convention. Actually, this is quite international regulations to retrieve the raw data, and then with the JSH, what we call the JSON SMD hub, to go to the here the CRG STA PST pre service test and enterprise management for the testing. This is where I'm working, and also the data process entities. There's for many. Okay, let's go to the next page. Next page. So there's another data view graph, Jpss ground segment high level architectures. So these pictures will be easier to visualize what the entire operations. Okay, from the frontline main satellite, and sometimes they send the data to the Merdom or Survivor, and the rest of the time the data are read by the TDIS. Okay, and from eventually it is controlled related to the ENSOF, and of course there's other place, Fairmont or AGS, Alaska ground station. But anyway, I'm working at the ENSOF here. So, and you could see here in ENSOF what we're doing. Okay, basically I'm in this group, ICF, GIP, gravity. Okay, in these sections, I am working on the interface computation facility. Okay, and you could see we're not the only one. There's also support FN, MOC, the fleet numerical meteorology observation observatory center, or naval Oceanic Observatory Office. Okay, NAVOCEANO. Okay, so there's support to many other facilities. Okay, but at the end, so here's where I am in the gravity ICF GIP. GIP means gravity information protocol. And gravity, what's gravity? Gravity means for the government resource for algorithm verification and independent testing evaluation. Okay, yeah, this is just a visual to show you the as the stored mission data flow. And unfortunately, this is actually a simulation. Next slide for the N20. N20, this is NOAA 20, and MPP, and okay, GCOM, and this is Japanese satellite. Okay, so you could imagine that actually we cooperate with the others, not just the USA satellite. Okay. And So I think this is just a more detailed log from the TDIS to the 5 ground station as well, and then to the C3S. C3S means command control communications system. Okay, that's why there's a 3 C's. That's why called C3. When you work in the NOAA and NASA, you are going to learn a lot of nickname. Okay, and up to the, and this is the where more detailed descriptions about what we're doing in the IPSA. Okay, integrated development product system, and where the ingest from, and then the products, and how we the CPERT is the is the performance evaluation tool. Okay, the common ground performance evaluations tools, and the product access will be the ND means MPP data exploitation, or then PDA is also the product distribution access, and the class is the comprehensive large array stewardess systems, and gravity. Okay, I have mentioned this many times because it is where I'm working daily, and the rest they are the military facility, navals, and FN, MOC. Okay, and the science data system. Let's go to the next slide. Okay, just another view graph to visualize to see more clear. I may, I think this is pretty much to describe more in detail. Okay, about the SMD flow. Just to describe what the ground sigma centers at the ends of is doing. Okay, where we get the data again from TDIS and the 5 ground stations as well. Okay, next slide. Okay, this is pages, I think is called Jpss program data products. So what am I doing? Okay, I'm trying to produce the Jpss level 1 data. Okay, and there's a few instruments I'm dealing with: VIRS, CRIS, ATMS, and OMS. Then the 4. Okay, and you could see from this map, this CRIS is cooperate, combined, as overlap with ATMS. Okay, and so our daily work is to produce the RDR raw rate record, and also the science data sensor data records, and then finally environmental data records. And here's in our system, the most of the software or in the hard drive. For the ingest right now is already migrated into the cloud system. Okay, but let's go to the next page, next slide. Eventually, we are going to migrate into what? Migrate into the cloud, okay, system. So we don't rely on the hard drive anymore. Okay, so this is plan. This NESDIS Cloud Pro for your vision. Okay, NESDIS stands for National Environmental Satellite Data Information Service. Okay, so this final. Could we go to the final? Skip the rest of the slide. Let's go to the Jpss product life cycle. Okay, I think there's a lot of free view graphs left. Just go to the Jpss product life cycles. Now, everyone work in the loop, work very hard to make progress. Okay, for lifetime. For instance, in this loop, okay, the algorithm kept on updating, and also the calibration parameters also kept on updating, and those instrumental ancillary auxiliary lookup datas, lookup tables parameters, okay, keeping updating. That's why we were very busy every day, okay, and trying to make the predictions and try to produce the science data more have a better quality and more accuracy. Okay. Now, this another page probably was not on the view graph, not on the PowerPoint I just sent before. Here just show you the constellation, how many international satellites in the sky right now. And we also work intensively with the European satellite as well, like a METAP, okay. And also we work with the JPSS Japanese satellite, okay. So let me summarize today's talk. The summary, okay. There's a product operations website there, so you could you could access this. I think this is public accessible, and the sensors. The purpose of this is actually a climate satellite with the instrument who keep on doing the research, try to improve, so we could observe the Earth's atmosphere and space events more clear and more precise. And it is a teamwork. That's like what I already show you my past experience, right? It really needs all type of talents, skills, and forces in every segment of the entire operations. Okay, actually, there's also a technical writer to work on the documentations. They're just English majors, not necessary to have any science background, but still could work in the loop. And so this, unlike other satellite, okay, this Jpss is going to serve until they fall to the ground to retire their mission, okay. And during these few years, lessons learned and the system will keep on upgraded. And the bottom line is that this mission is have to improve the safety of the human life and also curiosity satisfaction. Curiosity satisfaction. Thank you very much. So I think that concludes the talk.
Thank you very much, Dr. Jian.
You're welcome.
Very comprehensive description of all those programs. If you don't mind, we've had a few questions that were asked. First question that was asked is why were not the 4 satellites sent at the same time? Is it just because the technology was not ready, or is it a planned program?
Why? Okay. This Jpss mission actually is quite new. Okay. It's later than the GOES project. And you need to understand the instruments, the spacecraft, the mechanics don't stay forever. Okay. And that's why, and for instance, the MPP is going to fall very, very soon. Okay, we are monitoring the MPP daily. Okay, and so think about it. If we send all 4 satellites at the same time, right? Then what to do after their lifetime probably pretty much the same, right? Only stay probably like 10 years, right? And so this is the idea. The idea is to keep the mission going on continually, and also we are also we're trying to learn from and then I will show you the life cycle of the development. Okay, so we keep on make progress from our study, and that's why we are doing a lot of trending analysis and also trying to improve the algorithm. Okay, a lot of parameters we didn't consider in the past, but after the instrument getting more advanced, a lot of factors, even the general relativities phenomena, need to be considered into the calculation as well. Okay, and so this is a reason we don't send all of the satellites in one time. Okay.
Okay. Yes. Thank you.
You're welcome.
Another question was exactly what is your work currently? What are you working on at the moment at NOAA yourself?
Yeah. Okay. I think I have shown you the price of gravity ITP, right? So basically, what I'm working on is to deal with the L1 level data of the 4 instruments. Okay, views, ATMS, CRIST, and OMS to dealing with the L1 levels of data with the data ingested from the white sand. Okay, like what I have mentioned before, ENSOF acquired the data from those 5 ground stations. Okay, basically my work, I'm working on the software, so I'm developing the software tool to transfer the telemetry, okay, from every the raw data, okay, under the CCS convention to grab the raw data, okay, and also based on the algorithm to convert them into the sensing informations. Okay, so that's what I'm working on.
Okay, thank you.
You're welcome.
Maybe another question. You said that this data is made available to other countries. There are agreements with other countries to make this data available to everyone who needs it. Is that correct?
Yes, that's I show you the website. I think this is a link that open to the public, and yeah. And,
great. And well, so this observation allows you to predict, to do some weather forecasts and predictions, and see all those hurricanes, all those extreme conditions. Do you think that in the future, with all this technology, it will be possible to improve maybe the advanced warning about all those hurricanes and natural catastrophes that happen? Is there hope for an improvement in this thanks to this technology?
Yes, that is the goal, and we are working on. Okay. Yeah.
Okay.
That's why. Yeah. Okay.
Well, I'm sorry.
No, that's all right.
All right. Well, this then I don't see any more. Oh yes, there is another question here. Well, first, thank you very much. Very interesting indeed. The question is, what will you do with the former NOAA POES satellites, which were a failure, and how can they be destroyed?
Okay, actually, they just naturally retire now. The only what do you call, only when it's out for the ground, then stop the service. Unlike the satellite, I think it's for GPM. The satellite is when up to the stage when the instruments don't produce the useful science information anymore, then you're just waiting for discarding. And here actually, before, okay, that's why you know, from the J1 to the J2. J2 is going to launch next year. Okay, but of course, there's nothing is guaranteed. Okay, but you just based on our learning from our experience from the MPP. Okay, that is going to retire very soon or anytime actually. Okay, and also the experience of the right now the most active server is the J1 Jpss 1 or NOAA 20. Okay, now from now I could just tell you actually that even the application packet format have been changed, reformatted, so you could see the features getting updated. When we say update, actually it's kind of upgrade. We don't downgrade the features. Okay, and so we just trying to improve in every field from the huge teams of the scientists, research, and their analytical study to improve for every mission. So you could see right now, J2 is almost ready. Okay, but we are experiencing a huge amount of intense testing, try to make everything all right. And okay, and you could see we are always very careful, and even though the launch day is set to be September 30th next year, but because of weather condition at that moment and so on other issues, okay, then we also it's possible to delay. Okay, usually the time set usually only will delay. Usually will not be be set up earlier. Okay, so since we set the date to launch on September 30th, I believe that will go either on that day or delay for some weather uncontrollable factors. Okay.
Okay, thank you. Another question: Why 4 satellites and not 3? Is there a need for 4 satellites and not just 3?
Well,
would 3 not be enough? I don't know.
So this mission could continue even longer, right? For instance, that when the Jpss 3 is about to decay, okay, then the Jpss 4 are still going on, okay. So at this moment, I think the question is actually probably we would like it to go on forever, continue to have Jpss 5, 6, and so on. Okay, but right now the funding, the budget for the Congress is only hold. We only plan up to the Jpss 4. Okay, so this is the political and the funding issue. Otherwise, I think you certainly want the projects to continue forever. It's not just limited in 4. Okay, so but I think at this moment we just persuade the Congress to give up the features of up to the Jpss 4.
Okay. Another very interesting question. Will the quantic sciences help the project?
Okay. Occasionally I need to, when there's an emergency, I need to go back to the facility, that's for sure. Okay, otherwise we just tell you the VPN to the system, okay, to work with the teams, and we have a weekly meeting, okay. No, the facility is still not opened, and we just barely manage to work from home, but we are essential worker, so we still occasionally still need to go back to the facility to do what we cannot do at home. So yeah, this quarantine sucks, right? Yeah, it really affects the normal operation. Yeah, it's very inconvenient, right? And that's why we would like to this circumstance to go back to a normal as soon as possible. And I think, yeah, because of this, a lot of the plans have been delayed as well. Yep.
Somebody asked what was your cursus to get there? How did you get to this job, to working for NOAA? Maybe what was your career path? We in your CV we've seen all the degrees and the posts you've had, but what was this pathway to what you're doing now at NOAA?
Okay, so I you know, my major is in physics, okay, and I started to so it doesn't matter the work I have done in the industry or academic. Most of the work is really all related to the space science, okay, the sensors, and also my master degree actually is in high energy physics. My master degree thesis is working on the general relativity, and for the PhD is working on the laser engineering, photonics, and nonlinear optics. Those are just the background for actually the scientists. Okay, now in terms to the college student, when I think you students working on your master degree, okay, then that's why I show you something only related to my work, but not really. Oh, okay, and I already told you this. The entire mission need all sort of forces and all sort of the talents. And in the U.S. school, you get a lot of good training, either in the hardware space, craft, and also you are going to learn a lot of the space network technique. And so basically, it's depending on what skills you have that to fit into the mission required. Okay, so I just happened to be on the path, and yeah, I think that's it. That's why I just want to say that this in the school is the most efficient career training facility. So let's try to cherish that. When you are young, you could all develop all the skills you probably need for your lifetime. Okay, I just look at me. I think what I have done before, all the knowledge I have possessed in the past is just really very useful to what I'm working right now. Okay.
Okay. And maybe one last question.
Sure.
Can you tell us about the most unforgettable phenomenon you and your team have ever observed?
Well, okay. It's just like what I said. The issue is our data come from those TDRS and also the partners support. Okay, and once this coordination got broken, and like the ephemeris lookup tables get updated. Okay, and in the systems they were still using the old lookup tables. Okay, and it caused the entire operation to stop. Okay, and actually is because the just a tiny part of the coordination broken, that caused the entire operation to crash. And this is I think happened to the earlier of last year before the pandemic. Okay, and then we work day and night just trying to find the tiny mistake. Okay, with all of the team, including the star, and mostly okay. There's the science team is in the star. There's a facility in the the College Park. You know, College Park is where the University of Maryland College Park located. Okay, so this is another facility, and also there another active group for the science development is the ENSOF. Okay, so yeah, there's a unforgettable event at that time. And
okay. Well, maybe one last point that I've just seen. What is your motivation? What motivates you to do this job? What is your main motivation in this job?
Just I basically love the physics. Okay, I just feel that you know, I liked the interaction, even though my strength is the mathematics. Okay, but I only could consider when the techniques is related to the human being, then I could realize and I could get a feeling with it. Okay, so that's why for the mathematics, when you're just dealing with the dimension more than 4 dimension, I just cannot visualize that. I'm very confused. But once that I utilize the mathematical skills to do the detections, that is just so. I have started feeling, and it's just so interesting. It's just a curiosity, and like what I said, it's just a curiosity, satisfaction. That's my motivation, basically. I feel fun. The bottom line is that, yeah, interesting. That's why I just recommend usually just try to choose, follow your passion. Okay, you will certainly want to enjoy the work you are doing. It's not just right. Otherwise, it's quite tough. You will always just try to get over with it and try to finish the daily 9 to 5 hours. Okay, that is quite painful. But if you work with the passion you love, then then you don't mind. Sometimes we still need to keep working after the work hours. Okay, because you know the situation, the weather, hurricanes, they don't wait for you. Okay, it's not just because it's after the work hour, then the hurricanes stop happening, right? No. Yeah, and you just do it with your passion. Yeah, I think yeah, that's my motivation. Yeah, just for fun, interested, love it. That's it.
Thank you very much. What a perfect conclusion. You're obviously talking to a school where passion is the key word, the key motivator that we all share.
Yes.
So we do share with this passion with you totally. And I want to thank you so much to make us more familiar with all these complicated technologies. I mean, meteorology, oceanography. That's very, very technically interesting. Those missions of the satellites observation are just fascinating, and especially this availability of data, and all the hopes that you've brought by improving all the predictions that can be made on the weather predictions and all those hurricanes and catastrophes. So perfect link to the environmental issues. So I can understand your passion thoroughly, and you've definitely passed it on to us. I'm sure our students have been really interested, and it's been great. This conference will be made available on YouTube for those who would like to watch it later. So I'm sure they will make it available. Thank you again. Thank you so much. We're very grateful for your time and for sharing this with us. Thanks to all of you for joining us tonight. I saw we had many participants, and I want to thank you very much. sorry for the little technical problems that we've had, but this was live. Obviously, it proved that it was really lively, live broadcasted. That happens. Sorry about that. Maybe I want to give my special thanks to Florian Martin from IPSA for having made this even possible. Thank you, Dr. Jian. Thank you, everyone. And good evening and goodbye to all of you.
Well, thank you and have a nice evening. Okay, bye.
Bye.